So this stuff's due on Wednesday. So you okay on this stuff? We're doing the charts on this. So you'd have A and B, then you'd have the head loss in between, and then you're going to have elevation, pressure head, velocity head, and then the total, right? All right, now often you ignore velocity head, and you can do that for two reasons. One is it's not very big, so it's often ignored. But the other reason is that in a pipe like this, it'll be the same in both locations, A and B, so it'll just cancel out anyway. So you just want to, just figure out your elevation, which if you're out working, the surveyors will get that to you. You'll have a set of plans with the elevation on it, 120 feet, that's above sea level. And then you take the 100 PSI times 2.31 feet per PSI, and you get 231 feet. And then you just add everything up, and what, you get 351? All right. Now what we've been doing here this past week is figuring out how to find head loss, but for this homework, I'll just give it to you. So that's 20, and you take it away, and you get 331. Okay. And then the elevation at B is 210. So the 331 minus the 210 is 121. Okay, 121 feet. And then to find the pressure at B, you take that 121 feet and convert it 0.433 psi per foot. The way to do that. So that came out to be 52.4 psi. So that's the basic approach you'd take on these. Pretty common problem. So, you got any questions on that? Next one's really similar. The one thing on an open reservoir, the pressure up there is 0 because it's open to the atmosphere, so there's no pressure at the top. If anything, it makes the problem simpler to work out. That one should come out to be 21.65 psi, or whatever you want to call it, 21.7, 21.6, whatever. Okay. Got any questions on that one? So that's that one. All right, now so those first two are kind of just things to kind of get started with and used to that approach. Next two are maybe a little bit more involved, although this next one is pretty straight up. You could handle it with a table. I mean, there's actually this next one, there's a lot of ways to figure it out, but you could certainly do that with a table if you like. So that one there, you're going to have 52 psi. It looks like the pipe is flat, okay? So I would assume that to be the case. So you're going to have elevation, pressure head, and then velocity head, and then the total. And then you can have A and B, and then the head loss in between. So on this one, the elevations are 0. And what you're going to have on this one, we just want to find the head loss. Now you can notice that it's one pipe between A and B. So I don't think you're going to have to worry about the pipe size or about the velocity head, okay? Because it'll be the same in both locations. So you can just ignore that. So what you're going to have then is you're going to convert this stuff into pressure head. So that first one's going to be about 120 feet. So that's the energy you've got at A. At B, you can do the same thing, and it's 94.7. And that's actually 120.1 if you want to get technical about it. All right. So the way you're working this problem is you're kind of doing this, working your way into the middle, because if you know what the head is at A, and then you know what it is at B, you know the difference is the head loss. Okay. And so that's going to come out to be 25.4, that comes out to be. Okay. So that's the idea behind that one. We're doing all right with that? So what you're doing, you're adding up the pressure. Really, it just comes down to pressure head. You have to figure out that number, but that's going to be pretty straight up. It's just based on the 41 psi. So convert 52 psi into pressure head, it's 120.1 feet. And then do the same thing for at B. And then just find the difference. The velocity heads cancel out on both sides, and the elevation head is just 0 all the way across because it's a flat pipe. So there's no change in elevation. All right. You got any questions on that one? Okay. All right. All right, now the next one there, you've got a heck of a lot of head loss going through that, and you want to find the velocity of the water. That's what's going on in the next one. So what you've got, again, is I'll call this A, and I'll call that B, where the water comes out of the pipe. We want to find the velocity and the discharge. Now we're looking for the velocity, so you're not going to want to eliminate the velocity head from the relationship. It's going to matter. So you want to keep that in there. All right, and you've got the head loss in there. Okay. So what you've got there to start is, if you think of the top of the tank, there's no pressure up there, and the water's moving very slowly, so you can't assume that the velocity head at the top of the tank is 0. And then the elevation is 150. So the total energy is 150 over there at A. Okay, you're going to have head loss of 145. So if you take the difference, what you end up with is 5 feet of energy left over at B. Okay, and there's no elevation and no pressure head there because you've come outside of the pipe. So all that 5 feet is going to go into velocity head. And what that is, that's 5 feet, okay? So what you want to do then is to find the velocity that's associated with 5 feet, okay? All right, so to accomplish that, what you want to do is realize that velocity head is equal to v squared over 64.4. So you're just going to have to do some algebra to kind of figure out what v is if v squared over 64.4 is 5, okay? So you want to kind of back into what the velocity is. So you got 5 feet is v squared over 64.4. Okay, so if you multiply both sides of the equation by 64.4, you're going to have 5 feet times 64.4 is v squared over 64.4 times 64.4. So what I'm doing there, I'm just multiplying both sides of the equation by 64.4. And I'm doing that to get this lower term to cancel. So what I'm going to end up with here is that v squared is equal to 5 times 64.4, which is 322. Okay. So if v squared is 322, if I take the square root of both sides, I'll get the velocity. Because I know the square of the velocity is 322, so that means that the velocity is 17.4. Or 17.94, I think it is. Yeah. So 17.9 feet per second. So that's the velocity. Okay. All right, now if that's the velocity, if you want the discharge now, how much water is coming out of the pipe, you kind of go back in and look at the area of the pipe. Now the diameter of the pipe is called out at 2 inches. So the radius is 1 inch. Okay, and that's going to be 1/12 of a foot. So the radius, when you work that out, is 0.0833 feet. Okay. So if you know that, you can find the area in feet. It'll be pi times 0.0833 feet squared. Okay. So pi r squared will get you the area, and that's going to be 0.0218. So I have the velocity. What I want now is the area. So it's 0.0218 square feet. So now to finish the thing off, what you can do is say that Q, the flow rate, is equal to the velocity times the area. So Q is equal to the velocity, 17.9 feet per second, times the area, which is 0.0218 square feet. So that'll get you the flow rate. So Q is VA. So Q is 0.391 cubic feet per second. Okay. So that's the deal on that one. So there's a couple things going on there, of course. One is the whole bit finding the velocity head. You know, basically you've just got an elevation of 150 feet, and you got 145 feet of head loss, so that leaves 5 feet available for the velocity head. And that's v squared over 64.4, so you can solve for v. It's 17.9 feet per second. You can then find the area, which would be pi times the radius squared. Okay, the diameter is 2 inches. So the radius is 1 inch, which is 1/12 of a foot, 0.0833 feet. The area is pi r squared. So 0.0218 square feet. Multiply that by the velocity, you get the flow rate. So you get the velocity, and then you also get the flow rate. So we doing all right with that one? Now the next one's a little tricky too, but the thing on that is you've already done problem 9.5, which relates to that. So you can use your answers from the stuff I handed back to you on 9.5 to do the next one. Okay. And that just saves a bit of work. Because what we want to do here is find out what the pressure will be right there. And knowing what the areas are and the velocities is part of that. So the velocity at A is 3.63. And then the velocity at B is quite a bit higher because you're pushing the water through a constriction there. It's 32.7. Okay, so that's from problem 9.5 is what that's from. So you can start with that. Are we doing all right with that? Okay. Now, once again, you want to do a table. So what you have on the table is elevation, pressure head, velocity head, and the total. And you want to do A and B, and then you want the head loss in between. So that's what you're setting up for that. So what's going on there is there's no elevation change, so you can just call both elevations 0. The pressure head will be the pressure times 2.31 feet per psi. And so that'll get you the pressure head, and that comes out to be pretty big. That's 27.7 feet. Okay, the velocity head will be that 3.63 feet per second. You're going to square that and divide it by 64.4. And that's not going to come out to be too awful much. That's just going to be 0.2. So when you add the two together, you get 27.9 feet. So that's the energy that you've got at A. So we're doing all right with that? We got any questions on that bit? Okay, we're assuming there's no head loss, so that's the energy you've got to work with. Okay. Now the velocity head on the other side, you've got the velocity. It's going up quite a bit. It's 37.2 feet per second. Square that and divide it by 64.4, and you get 16.6. Okay. So just making the water go faster requires a lot of energy. All right. right? So based on that, you can figure out what the pressure head's going to be, because you got 27.9 and you got to use 16.6 for velocity head. So what you're left over with then is 11.3. So that's what the pressure head is. So you can just convert that to pressure and figure out what the pressure will be, and it's 4.9 psi. So just by pushing the water through that venturi, as it's called, you're dropping the pressure by about 7 psi. And the reason is you're making the water go a lot faster, and when it goes faster, the energy required for the velocity head goes up, and it has to come from somewhere, and where it's coming from is pressure. So that device can be used to get the water moving so fast that the pressure you can drive the pressure to a vacuum, and that's how chemical feeds work, is by doing that.
What's it called again?
Venturi. It's named after some scientist who studied it. So, you got questions on that? All right. Okay, the last two relate to hydraulic grade line. What that is the sum of all the energy in the system plotted up as an elevation. Okay, so what you have there is a map of a pipe coming down from a reservoir going to these different elevations on the left. You're also given the pressure reading on this. Now we're going to ignore velocity head because it's probably pretty small compared to the scale of the map we're looking at. So we're going to ignore that. So all you got to do here is just take those pressures, 13 psi, and then multiply it by 2.31 feet per psi, and convert those pressures into feet. So that first one comes out to be 30. Okay. So you've got 30 feet of pressure head there, as it's called. You can start out at 160 and go up 30 feet. And where you're going to end up here is up at 190, which is the sum of 160 plus 30. So what you want to do then is just do that process 2 more times. You know, no big deal, just plot it up. And just plot the points together. And you'll end up with a hydraulic grade line. It starts right here at the edge of the reservoir at that elevation, and then it'll just work its way down is what it'll do. So we're doing all right with that? Just connect the dots, and you get a hydraulic grade line. And that's something you can plot up on a map and have a look at it. If you're doing a storm sewer, if the hydraulic grade line goes above the top of one of your manholes, you got a little problem there, because you're going to have what we call a surcharge manhole, where the water's going to come out the top of the manhole, and that's not good. Okay. All right. Okay, then the last one there, all I want is a sketch. That's the key word. So just tell me what's going to happen with that hydraulic grade line if the valve is closed. And remember, if the valve's closed, you have no head loss. And then when you open the valve, you do have head loss. I mean, that's basically all there is to this one, is just kind of sketching something up that indicates that. For a closed valve, there's no head loss, and for an open valve, there is. Okay? So real simple lines on there should be enough to get that done. Got any questions on that one? Okay. All right. What I'd like to do is to finish up. If we got any other questions on this stuff? All right. All right, let's finish this stuff up for these homework problems, or not homework problems, for these examples where we have reservoir flowing down to a hydrant. Let's look at page 115 when we have C that's different than 100. Okay, so let's have a look at that. So this is, I think, page 115, if I'm not mistaken. So now we got C140. And we want to find the pressure at the hydrant. All right, now this table gets filled out pretty, in very similar ways every time. We're working through this same physical setup over and over again. So once again, we got 320, we got no pressure head. We're going to ignore velocity head. So we're going to have 320 feet of energy here. Okay, now we need to find the head loss. Now this time we're going to have to find the head loss for C140. Okay, so to find the head loss for C140 pipe, what you need to do is to find the equivalent flow. So that's the actual flow times 100 over C. Okay, so you can find the equivalent flow by taking the 700 gallons per minute times 100 over 140. Yeah, and that'll come out to be 500, right? So now when you go to the table, you use 500 gallons per minute, not 700. So the deal with this is when you're working on the table, you use the equivalent flow. Okay, so we're going to use 500 gallons per minute. And yeah, so we got 8-inch pipe, 500 gallons per minute. So we just go to 8-inch pipe, and not 700 this time, but 500. So that's right there. So that the head loss there is at 0.82. Okay. So that's 0.82 feet per 100. Okay. All right, so the head loss then is 0.82 feet times, it's 920 feet long, so that's 9.2 100-foot lengths. That's how I think about that. And that'll come out to be 7.54 feet. All right, so So if that's the case, we're going to subtract that. So that's minus 7.54. So what we're going to end up with then is 312.46 feet. Okay. And then we've got 240 feet of elevation at the hydrant. So based on that, we can back in and figure out what the pressure head is. It's 312.46 minus 240. So that's going to come out to be 72.46, I think. So that's feet. So we'll take 72.46 feet, and we can convert that into PSI. Multiply that through, and we'll get 31.4 PSI. So it's real similar to the one we did where C's 100. We just have to modify how we find the head loss is about it. Okay. So we're doing all right with that? Now the next one, we're going to consider velocity head on this one. So the table is going to be filled in a very similar way. It's 320, 0 for pressure head, 0 for the velocity head, because that initial velocity is at the top of the tank, and that would be very, very low. So we could ignore that. So there'll still be 320 feet. The head loss will stay the same, because we're pushing the same flow through the same pipe with the same C. So what we're going to end up with here, once again, is 312.46 feet. Okay. We've got 240 feet for elevation at the hydrant. So it fills in very much like the one up above. Okay. All right, now we've got two flows. We need to consider velocity head. So the question here is, which flow do we use to find velocity? Are we going to use the actual flow at 700 gallons per minute or the equivalent flow at 500 gallons per minute? Okay. So we have to decide which flow to use. All right. Now, the answer to this lies in the fact that you've got Q equals VA, so the velocity is just the flow rate over the area. The velocity is based on taking a flow and pushing it through a certain size opening, and that leads to what the velocity is. And where I'm going with this is the C value doesn't affect the velocity. If you got an 8-inch pipe and you're pushing 700 gallons per minute through it, it doesn't matter what the C value is. The velocity will stay the same. Okay? So the answer to this is you use the 700 gallons per minute because you're pushing that much flow through an 8-inch pipe. Okay. And the velocity then will be 4.47 feet per second. And you can find that off the table there. 700 gallons per minute, 8-inch pipe, right there. So don't be fooled by the C on that one. You use the equivalent flow to get the head loss, but not the velocity, because the velocity just depends on the flow rate and how big of a pipe you've got. Okay. So you can run the numbers on the velocity head, and it just doesn't come out to be very much, you know. When you take 4.47 feet per second and you square it, and you divide it by 64.4, you just get 0.31 feet. That's all you get. So, you know, once again, the velocity head just doesn't make a whole lot of difference. And that's going to be the case for most of what we do. You know, there isn't, I can't really think, other than a Venturi or something like that, where you've really got high flows, I can't really think where it's going to make that huge of a difference. Okay, so this is going to be 72.15 feet of pressure head. Okay, and up above it was 72.46. Okay, so they're very, very small differences on account of velocity head. So the pressure head for this case will be 72.15. In the example above, it was 72.46. So very small change. Doesn't make much difference. Okay. So if you've got 72.15 feet of velocity head, what you do to convert it into pressure is just multiply it by 0.433 psi per foot, and that will get you the pressure. And instead of the 31.4 above, now it's 31.2. So you're getting 0.2 psi difference by considering velocity head. Just not a big deal. You hardly would pick that up on a gauge. You know, if you've got a needle type gauge, you're not even going to notice it. Okay. So it's the same problem. You just pick up a little bit of velocity head there. The one thing on this is don't use the equivalent flow, use the actual, because the velocity is just dependent on the flow divided by the area. That's it. Okay. I think we're about out of time here. Okay, now I did, for whoever wants to be doing that makeup quiz, there's copies down there in the Red Cedar Hall 111 testing center. I'll leave that down there next week. And what that is going to cover, and that'll get you up to a 70, okay, on the test. So if you got below 70%, you can get up to 70 with that. And what that has is the density and specific gravity on it. It has the real important concepts that we use. So density and specific gravity, it's got the relationship between height and pressure. So just using those 0.433 and the 2.31 conversions, and then it's got that the force is the pressure times the area. So that's what's on that quiz. So it's abbreviated. It's not like a full midterm. It's just got those 3 important topics on it. Okay. So we're doing all right with that? Okay.